Hello again. This is Math 2232 coming to you from the College DuPage. And the title of this lecture is called Improper Integrals. As always, please be an attentive learner while watching this video. By way of introduction, the term improper doesn't mean anything's wrong with it, but we're kind of stuck with the term. And there's actually a strong analogy that exists because you call this, if you have 12 over 5 in your school, you call this an improper fraction. And that meant the numerator was bigger than the denominator. It doesn't mean there's anything wrong with this number. In fact, this is one of my favorite numbers. But a proper fraction is one where the numerator is smaller than the denominator. And so that's the difference between proper and improper fractions. Again, both of them are great numbers, and when we talk about improper integrals and proper integrals, they're both good things. Now, back in Calc 1, when you studied the fundamental theorem of calculus, you learned the fundamental theorem of calculus, which said if a function is continuous on the interval AB, and this was a finite interval, A and B were finite numbers, then the definite integral from A to B of f of x dx was equal to capital F of B minus capital F of A, where capital F is any function, any antiderivative of lowercase f of x, and that was true for all x in AB. Now this is considered a proper integral, but the if part tells us what makes it proper. The function has to be continuous. That means you can trace it without lifting your pencil. And the interval that it's defined on has to be finite. That makes something a proper integral. Going directly from this, there are two things that can make an integral improper. You can have the interval of integration being infinite instead of finite, or you can have a discontinuity of the function in the interval of integration. And so there are two flavors of improper integrals. We will talk about them both within the next couple of lectures. And continuing with our example, let's evaluate the following integral, and this is the definite integral, actually the improper integral, from 1 to infinity. The reason I didn't call it a definite integral, because infinity is not a real number, but this is 1 over x squared dx. And if I graph 1 over x squared dx, and I'm going from 1, so this is where 1 is, it goes out and you see that this thing drops dramatically towards 0. So this is an instant enough looking integral, but because infinity isn't a real number, we can't just plug infinity in to get an answer. So to see how we're going to do this integral, let's think about this as an area problem on the interval 1 to infinity. And let's just we can't do that because we can't plug it in using the fundamental theorem. But let's step back and ask instead, what would be the area under this f of x on the interval from 1 to t, where t bigger than 1 and t is finite? Now this could be 5, this could be 10, this could be a million. T could be any number, however big. In fact, it could be the national debt, which is probably around, actually, I don't know what the national debt is, but it could be the biggest number that you ever have thought about. But anyway, let's just do this. So a sub t is equal to the integral from 1 to t of 1 over x squared dx. So we add 1 to the exponent, divide by the new exponent, and we get minus 1 over x. And then we plug in 1 at the low end and t at the top end. Now, since there's a minus sign here, when we do the signs, we're going to get minus 1 over t, and that's minus minus 1, which when we simplify is 1 minus 1 over t. But now we say, well, yeah, but t could be as big as I want. So what is the limit as t tends to infinity of a sub t? And the limit as t tends to infinity of 1 minus 1 over t, well, that the limit of the sum is the sum of the limits. And so 1 is just 1, but 1 over t gets closer and closer to 0 as t gets bigger. So this limit is 1. That means that this area under this curve is 1 all the way to infinity. And that's how we do an that's how we do an improper integral here. We go from 1 to infinity, 1 over x squared, and that's the limit. We replace this by a variable, and we do the integration, but then we still take the limit, and the limit is our answer. Okay, so this is how we deal with integrals of this kind. And surprisingly, the area under curve on an infinite interval was not infinity. In fact, it was a small number. It was only 1. That won't always be the case. Sometimes the interval will be infinite. So let's get some terminology out of the way. Please understand these because I'm going to ask these when I ask questions. So we'll call an integral convergent if the associated limit exists and is a finite number. So we don't get plus or minus infinity, but there's two things make it convergent. The limit exists and it is a finite number, and it's not plus or minus infinity. If it's not convergent, it is divergent. That means either the limit doesn't exist or it is plus or minus infinity. Now, we can have different things though. So we can look at this, that the integral, the improper integral from a to infinity of f of x dx is equal to the limit as t tends to infinity, and this is the integral from a to t f of t dt, provided the limit exists and is finite. That's when we had infinity on the top. If we have infinity on the bottom, the improper integral from minus infinity to b of f x dx is the limit as t tends to minus infinity, and t is the limit on the bottom, provided the limit exists and is finite. And if both this, from minus infinity to c, f of x dx, and the integral from c to infinity, f of x dx, are both convergent, then the improper integral from minus infinity to infinity f of x dx is the integral from minus infinity to c f of x dx plus the integral from c to infinity f of x dx, where c is any number. Now this is kind of subtle, and we're going to do some examples of this, but that's what this means. So if this and this are both convergent, then so is this. Both integrals have to be convergent in order for this integral to be convergent. And if either of the two integrals is divergent, then so is this integral. So now it's time for you to do a problem. Determine if the following integral is convergent or divergent, and if it's convergent, find its value. Now this is often how I would ask an improper integral question. So this is the improper integral going from 1 to infinity of 1 over x dx. You know what to do. Let's see how you did. Now here I have graphed 1 over x, that's the red curve. And I've also graphed 1 over x squared, which was the first one that we did. And we knew that this area here was finite, but let's talk about what happens in this case. So this is what you should have done. You should say the integral from 1 to infinity of 1 over x dx is equal to the limit as t goes to infinity of the definite integral from 1 to t, 1 over x dx, and then we compute the integral. Now the integral, the antiderivative of 1 over x is the ln of, and it would be the ln of absolute value of x, but t is a positive number. And so I'm just evaluating this at t and subtracting ln of 1. Now the logarithm, as you know, is a very slow growing function, but it does tend off as you go to infinity. The number just gets bigger and bigger, and it goes to infinity. So when you plug these numbers in, you get the limit as t goes to infinity. This is ln of t, which is going to be infinity, minus the ln of 1, and the ln of 1 is going to be 0. So you see we get infinity as this limit, so the limit is infinite, and so the integral is divergent. Now, so if we get back thinking about the area, we said, oh, this is divergent, but this is convergent. But really, there's not much difference between the two. So there's something really going on with infinity, isn't it? And you might really say, well, if this one was convergent and this one is divergent, is there a breakpoint where things change from being convergent to divergent? And there is. This is the fact. This is also a theorem. So if a is greater than 0, and a can be any finite number, then this improper integral from a to infinity of 1 over x to the p, and p is, we're talking about that being also a variable, dx, but it is a number. It converges if p is bigger than 1. and it diverges if p is less than or equal to 1. You want to remember this fact, and in fact memorize this. This is important. So what we're really saying is, does the integrand go to 0 fast enough? And this answers that question. And the proof is actually done by a calculation. Let's compute this integral. And I kind of skip some steps here. But what happens is, this is the improper integral from 1 to infinity. That's x to the minus p dx. So what we do is we add 1 to the exponent. That means it's, instead of minus p, it is 1 minus p. And divide by the new exponent. That's 1 minus p. And if I plug the numbers in, and I did a little bit of shorthand here, and I really should take the limit. I didn't write that, but if I take the limit and I plug in the limits, you will get these results. So when you put 1 in here, you will get this, and the other one will go to 0 if p is bigger than 1. If p is less than or equal to 1, this will blow up, and this will be an infinite area. And you should note from this discussion and the previous discussion that the lower limit actually doesn't affect the convergence or divergence. This could be any number L, like I had before. Now, it will affect the answer, but it doesn't affect whether it converges or diverges. Here's another problem for you to do. Determine if the following integral is convergent or divergent. If it is convergent, find its value. And notice that I keep asking the question this way because that's the way I'm going to ask the question on an assessment. So this is the improper integral from minus infinity to 0 of 1 over, this is the square root of 3 minus x dx. You know what to do. Let's see how you did. Okay, so you say that this limit is the limit as t tends to minus infinity of the definite integral from t to 0 of 1 over this. And again, now you do the integration, and you see how you really have to be good at this integration. But what you're going to do is you add 1 to the exponent and divide by the new exponent, and you have to do a change of variable here. So the antiderivative of this is going to be negative 2 square root of 3 minus x. Make sure you follow this, and I'm evaluating this at 0 and t. So I plug in the numbers before I take the limit. So when I put 0 in there, I get minus 2 square root of 3. But when I plug in 2, I get 2 times the square root of 3 minus t. So when I take this limit as t tends to minus infinity, I have this number. But as t goes to minus infinity, this is like the square root of, and you got a minus times a minus. This becomes infinite, and so this is infinite. So the limit is infinite, and this integral is divergent. Here's example 4. Determine if the following integral is convergent or divergent. If convergent, find its value. You see, I'm always going to ask questions like this. But this one goes from minus infinity to infinity of x e to the minus x squared dx. You know what to do. Let's see how you did. Here I drew a picture of this, and you can see that if I graph x e to the minus x squared, it damps out. If I have a negative, and x squared is always going to be positive, but x is going to be positive or negative. So I'm going to get negative over here and positive over here. And so that's what the picture looks like. So in this case, we got infinities in both limits. And so what we're really going to do is we're going to do a computation. We're going to say, what happens when you go from minus infinity to 0 of x e to the minus x squared dx, plus what happens when you go from 0 to infinity of x e to the minus x squared dx. I picked 0. I could have picked any number between minus infinity and infinity, but this is convenient to calculate. So what we're going to do is we're going to do a u substitution. We can let u equal minus x squared, and then du is going to be minus 2x dx, and you can work through and do this calculation. In fact, make sure you can do this calc 1 calculation. So this is going to be the limit as t goes to minus infinity, and this goes from t to 0, x e to the x squared. I change the variable, and I end up with this is going to be the limit as t tends to minus infinity of, and this is the antiderivative of that, so this minus 1/2 e to the minus x squared. I plug in 0. When you plug in 0, e to the 0 is 1, so that is just minus 1/2. But when I plug in t, I get 1/2 e to the minus t squared. But now I take the limit as t tends to minus infinity. Well, as t tends to minus infinity, you can see that this goes to this is tending to minus infinity. That goes to 0. So this is just minus 1/2. So the first integral is convergent. We have to check to see if the second one converges. So now we're going to do similarly the integral from 0 to infinity, x e to the minus x squared. Then does this limit? We will do the same antiderivative, plug things in, take the limits, and we get 1/2. So you see, this converges and this converges, so the whole integral is the sum of the two, and it's 0. And from an area standpoint, you can look up here and say, oh yeah, that makes sense to me, that the negative area here would cancel out with the positive area there. And in fact, in this case, it does. Here's another problem for you to consider. Determine if the following integral is convergent or divergent. If it is convergent, find its value. See, the directions are always the same. And this is the improper integral from -2 to infinity of sine of x dx. You know what to do. Let's see how you did. Okay, so what we'll do is we'll go from -2 to a number t, and we'll take the limit as t tends to infinity. Now that is the sine of x. The antiderivative of the sine of x is minus cosine of x, and I'm evaluating that at -2 and t, and this is minus x. Make sure you follow this calculation, but this is the limit as t tends to infinity of, and we'll get some minus action, so we get cosine of 2. Now cosine of 2 is a number. It's an irrational number, and I know what it is. You can approximate this by plugging it into your calculator, but this is cosine of 2 radians. You just leave that alone because that's the exact number. But then a minus cosine of t. But then I say, what happens to cosine of t as t tends to infinity? I really should have graphed, I guess I was really graphing this function. Let's just talk about the area. So what happens as cosine as t tends to infinity? Well, as cosine goes, it's going to range between 1 and -1 and 1 and -1 and 1 and -1. This limit doesn't exist because it doesn't get close to and stay close to a number. The limit doesn't exist, so the integral is divergent. Here's another problem. I'm asking you to evaluate the improper integral from 1 to infinity, and this is 1 minus x whole times e to the minus x dx. You know what to do. Let's see how you did. Now, I actually have to do a quick flashback for you to do this integral. You might have done this automatically, but you have to remember from Calculus 1 at the College of DuPage a thing called L'Hopital's rule. And what this tells us is that if you have a limit as x tends to c, and c can be plus or minus infinity even, and this is f of x dx, that's the same thing as the limit as x tends to c of f prime of x over g prime of x. And so if you get infinity over infinity, or 0 over 0, or something like that, or even 0 times infinity, there's all kinds of things that you can get here that you can take the derivatives and evaluate it that way. And so this is L'Hopital's rule, and you actually have to use that to finish this problem. Okay, so here's what you're going to do. Now you see this is 1 times e to the minus x. That's an easy integral to do. But the next one is minus x e to the minus x. That's one you have to use by integration by parts. You see how this course builds on things that we've learned. So we're using integration by parts with dv equal e to the minus x dx and u equal 1 minus x to integrate this integral. And so we will get minus e to the minus x times 1 minus x minus the integral of e to the minus x dx. And so when I do all of this calculation, I get x e to the minus x plus c. Now I can take c to be 0. because whatever I take it would subtract off. But this is integration by parts. So you see this was dv and this was u. And so v is minus e to the minus x. And so what happens is you will get, actually it is e to the minus x. And so what will happen is here you'll get uv minus the integral of v du, and I'm evaluating both at these points. But when I do that, I'm going to get the limit as b tends to infinity of b over e to the b. Now both of these tend to infinity, so that's where we have to use L'Hopital's rule. So using L'Hopital's rule, I can evaluate this first limit, and that becomes the derivative with respect to b is 1 over e to the b. As b tends to infinity, that is 0. And when I put 1 in here, I just get minus 1 over e. So I get 0 minus 1 over e. That means that the answer here is minus 1 over e. Here's a picture of the graph of the function and the area that we computed. And since it's underneath the axis, that is minus 1 over e. Here's another problem. This goes from minus infinity to infinity. So find the improper integral from minus infinity to infinity of e to the x over 1 plus e to the 2x dx. You know what to do. Let's see how you did. All right, so we're going to again use 0 because that's a convenient point. So this integral is going to be going from minus infinity to 0, and this is going to go from 0 to infinity. Now, if you look at the graph of this will be kind of a bell-shaped curve. Here's what it would look like. And the way you do this is by doing a substitution. And in fact, this substitution here is that you can let it ends up being u is equal to e to the x, and then this is 1 plus u squared over, and that is du, and so that's the arctangent. That's calc 1 again. So this is the limit as b tends to infinity of the arctangent of u, which is e to the x, and I'm evaluating that at 0 and b. And here I get the same thing, except the limits are different. It's b and 0, and that's the limit as b tends to infinity. Now, the arctangent, or let me do it a different way. When I get 0 here and plug it in, that's the arctan of 1, which is known to be pi over 4. And then here also I'm going to get a minus pi over 4 when I sub that in, because that's the arctan of 1. But then I'm looking at the arctan of b, or of e to the b actually, and as b tends to either minus infinity or plus infinity. Now, as b tends to minus infinity, the arctan tends to minus pi over 2. This is from your trigonometry that you remember. And as you tend to positive infinity, it tends to pi over 2. So we substitute those values in. We get pi over 4 minus yeah, we get pi over 4 here. So that's going to be if we rearrange all of these things, this is what we will get. And when you tend to minus infinity, this tends to be e to the minus infinity tends to 0, so that is going to be pi over 4 minus 0. This is going to be pi over 2 minus pi over 4. You do all the calculation, you get pi over 2. Now, with this example, I'm just showing you that this is a physics problem, and it really does come up. We're trying to have the work required to move a space module in an unlimited distance from the Earth, and we calculate it here, and it turns out the physics will tell you that it is an improper integral. So I'm just trying to show you that there are applications, and we will talk about work later in the course, and this application will make a lot of sense then, but I'm just telling you, yes, you need these improper integrals in your physics. And the last application that I'm going to talk about here involves a revolution of solid. We really haven't talked about that, but this is something called Gabriel's horn. And so you have an infinite horn here. And what I'm really showing you is if you calculate the volume, this is kind of a preview of coming attractions, but if you calculate the volume, you'll get a finite volume, but an infinite surface area. That's very surprising. Infinity is a complicated topic, and there are surprising results. More about this later. This is those last two examples were previews of coming attractions. In closing, for now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.